All right, so today we are talking about the behavior of polynomial functions. And this is actually my second attempt at this video because the first day we taught it, we wanted to tweak some things we kind of decided as a class. Before we dive into the notes section here where we have our definitions and this chart and everything, I want to back up. If you missed class, we kind of first did an explore activity that I think will really set up our understanding of the notes better. So we did a quick turn and talk. What patterns do you see when observing the functions in the graph? So if we look at the right here, we kind of observe them as a class and notice that, hey, all of these generally point up. We have on the left side it points up, on the right side it points up on all three of these graphs. We also notice that the leading term has a positive or not a positive exponent, an even exponent, right? We have x to the fourth power, x to the sixth power, and x to the fourth power. All of those are even. So we want to start thinking of that as an even shape there. Then if we repeat that exercise for this set of graphs, we can kind of look at the same thing. This time, our graphs start low over on the left and go high over on the right. And if you look at the degree of each of those polynomials, we have a third degree, a fifth degree, and a seventh degree. So those are all odd degree polynomials. So already we're kind of start building. We have an even shape where both ends point in the same direction, and we have an odd shape where they flip. Now, we also started comparing a couple of things. And in this comparison, we have this orange group here, where on both ends of our function we point up, and then this green group, both ends of the function point down. And the key difference there is in our leading term. Notice how all the degrees are even, fourth degree, fourth degree, fourth degree, and fourth degree. But on the left here, in our orange group, we have a positive leading term, and in our green group, we have a negative leading term. And so what that negative does is it flips our function from being both sides up to both sides down at our end behavior. Similarly, with our odd degrees, we looked at that where we have the purple over here with positive leading terms and odd degrees, positive leading term, odd degree. And we have our blue group over here, which had a negative leading term and odd degree. And notice the difference in the shape, right? We started low on the left, ended high on the right for our purple graphs, started high in our blue graph, and ended low in our blue graph. So I want to kind of take this idea and then formalize it in some notes here. So let's start off by getting down this definition for end behavior. So end behavior describes the behavior of the graph of the function at the ends of the x-axis. And so what this means is as we move all the way left and as we move all the way right, we want to describe the end behavior of our functions. So what we kind of summarized here, or what we learned in our turn and talk and want to summarize here, we can put in this table. So when we have an even degree polynomial, so our degree is 2, 4, 6, 8, 10, whatever. If that leading term is positive, okay, I'll abbreviate that POS period. As we move left, our graph increases forever. And as we move right, our graph increases as well. When that even degree polynomial has a negative leading term, all that does is flip our graph down, where as we move left, we decrease forever, we move down to negative infinity, and as we move right, we move down to negative infinity as well. Okay, when we have an odd degree and a positive leading term, as we move left, our function value decreases to negative infinity. As we move right, our function value increases to positive infinity. And now those will flip as well when we go into the negative section. So odd degree, negative leading term. As we move left, we increase to positive infinity. As we move right, we decrease to negative infinity. So one thing I want to add to our notes, which did not come into play the first time we ran it through, but I think will be really helpful to us is this kind of translation description here. And you should have space to put this into your end behavior definition notes. And it's really going to help us describe the end behavior when we get to examples. But basically, if you want to say the word right or describe as the graph moves right, here's the notation that's going to show up on end of course tests, ACT, practice problems. It's going to say, hey, as our x goes towards positive infinity, and if you think about your xy coordinate plane, okay, if we have our coordinate plane here, we got y here, also is noted as f of x. Okay, y and our function output are the same thing, and x is our right and left. Okay. As we move towards the right, as our graph goes on forever to the right, we're moving x towards positive infinity. And as we move to the left, we're moving x towards negative infinity, right? Positive to the right, negative to the left. So the same thing can be said with our function outputs, f of x, going towards positive infinity. That means up, right? F of x towards positive infinity. And you don't have to sketch this. I'm just adding it for some visualization. And to move down, f of x would be going towards negative infinity. Okay, a couple other definitions we want to get down is a local minimum and local maximum. And both these are really close, just with that one word flipped. A point within an interval at which the function has a minimum value, that's a local minimum. If we look at this little image here that's on your sheet, I'll use local minimum in blue, and we have a local minimum at point A here. And the reason we call it local is because if we look at just a small section of this graph, like let's say we cut off everything over here, okay, A is a minimum value. However, if we look at the graph as a whole, our graph continues down to negative infinity as we move to the right. So there are values that are lower than A. However, in this spot here, we have a little dip, a little valley at A, and so we're going to consider that a local minimum. And the same can be said for B, a local maximum here. Even though as we move to the left, the graph does increase forever, we have higher values than the value of B. We do have a hill at B, and kind of a peak value in that localized area. So let's start applying some of these concepts to some examples. And the first thing I want to do is make sure that we have add some arrows to the end of our graphs. I should have put that on there for you, but that just implies that our function moves on forever. So example one, we want to identify the specified features for the function using the graph. Our function is x squared plus x minus 2. The first thing we want to do is find our end behavior. So we're going to use that notation that we used, or that we kind of talked about a couple slides back. And here is kind of how it's going to look. First thing I want to do is describe my function as I move to the right. Okay, so we are going to say, if we look, as we move right, our function is increasing as we move to the right, right? So we're going to say that my function value goes towards positive infinity, right? It's moving up as x goes towards positive infinity. And it might be confusing at first, but we'll get good practice with this. But think about, all right, if we translate that, my graph is moving up as I'm moving to the right. Go back, we see, all right, my graph is moving up as I move to the right. So the next thing we can describe is that left behavior. And we look here, as we move to the left, okay, our graph is also going up. So in this case, f of x goes towards positive infinity as x goes towards negative infinity. Okay, so we'll get more practice with that end behavior stuff, but that's going to be a pretty difficult portion of our understanding here. Then let's circle any local minimum and box any local maximum. In this case, we just have a local minima down here at the bottom point. There are no local maxima to find. And finally, on these intervals where the graph is decreasing and increasing, I'm going to scratch that from our notes today. And I want to handle that kind of graph behavior in later lessons as we kind of start modeling different situations. So let's move on to example 2. First things first, let's correct kind of my mistake here, or add a little support for ourselves here, add some arrows to the end of our graph. And then we are going to analyze x to the third power minus 2x squared minus 5x plus 6. And let's start with that end behavior. If you want to try this on your own, please feel free. But let's start talking about as we move right, what is our graph doing? And as I go to the right here, as I look going towards positive infinity on our x, it looks like our graph continues to increase forever. So f of x goes towards positive infinity as x goes towards positive infinity. And if we look at our left side, okay, as I go to the left forever, it looks like my graph goes down forever. So f of x approaches negative infinity. In this case, it's going downwards as x approaches negative infinity. Then we can circle any local minimum and box any local maximum. We have a local minimum down here, right around x equals 2. And we have a local maximum at roughly x equals -1, because we have a valley at our yellow and a hill at our green. Oh, and again, one more thing. Let's cross off that intervals where graph is decreasing and increasing, and let's hit that at a later lesson. All right, last one here, example 3. Let's add in our arrows to the graph to make sure that we have some nice scaffolded supports. And we are looking at the end behavior here. And one thing I want to point out that I didn't in previous ones is you can verify that this function makes sense by looking back at your end behavior chart. Right? We had negative x to the 4th power as our leading term. So we have a negative graph, even degree polynomial, both are pointing down. That should pass our kind of sniff check there. So try this on yourself to identify the end behavior, then come back, check your work. But it looks like as we move right, the graph goes down. As we move left, the graph goes down. So our statements are very similar. F of x approaches negative infinity as x approaches positive infinity. And f of x approaches negative infinity as x approaches negative infinity. Right? Whether I'm moving to the right, as in this case, or I'm moving to the left, as in this case, my graph is going downwards. So we're approaching negative infinity as x moves in either direction. Okay, then let's use our blue to circle any local minimum. We have one here. And box any local maximum. We have 2 of them. We have a max here, box that, and a max up here. Oh, and again, feel free to cross off these intervals where decreasing and increasing. Okay, last thing we want to just kind of firm up, or to go through to firm up our understanding, is we should be able to predict the end behavior. Actually, we should know the end behavior simply based on the function we're given. And if we think back, you guys jotted down this nice chart, okay? This will help you kind of sketch and then describe what that end behavior is. So in this first example, we have an odd degree polynomial. If you look at that leading term, we have an odd degree positive. So we're going to go down as we go left and go up as we go right. And the notation for that, if we continue practicing that, it's going to be f of x goes towards positive infinity as x goes towards positive infinity. Okay, f of x goes towards negative infinity as x goes towards negative infinity. And again, that means as we move right, we're moving up. As we move left, we're moving down. And let's go ahead and try that in example 6, because I'll come back to 5 and 7 once I have some more space. Example 6, we have an even degree polynomial here. So if we look at our chart and it's positive, we look at our chart, both of our end behaviors are going up. And so maybe we can write this in a different order if we want to. We know that f of x is approaching positive infinity on both sides. So our graph is increasing on both sides here. And then we just want to write in those final behaviors. So as we move to the right, so as x approaches positive infinity, and as we move to the left, so as x approaches negative infinity. All right, these next two, I want you to try it on your own and notice how we have negative leading terms this time. So try to sketch the end behavior and then write out this notation, and I will unpause my screen once I have the work done and you can check your work. All right, here's my work for example 5 and 7. Check it out, see if we have any more questions, make sure our work is caught up. And then if you're making up the notes today, make sure that you check Canvas to see what our practice problems are.